last class we have started design for shear, and today we shall continue design for shear because we have started one problem solving. So, this lecture design for shear that we shall continue today. Let us just review the problem which we have started and just review it. So, we have two brick walls, we can take it this one say 250 millimeter width, having so many, just for clarification we have made it like this, there are so many beams 3 meter spacing covered by the roof or slab. So, this is your different beams, but we have constructed these beams integrally with the slab. So, we can take the action of T beam. So, each of them will be T beam and which has width of the wave, depth of the flange, width of the flange and depth of the wave also. Okay. So, before we come to that, let us see that few thing what we have done. Already you have in your notebook, but anyway I think it is worth mentioning. A series of beams placed at 3 meter centers are supported on masonry walls, which we have already shown. The slab thickness is 125 millimeter and ribs below the slab are 250 millimeter wide. The depth of the wave is 250 millimeter, provide tensile reinforcements and also design for shear, because we do not want to do it separately for flexure and shear, we want to do the same problem for flexure as well as shear. And width of the masonry wall, that is 250 millimeter, that we have done. We have calculated loading. So, dead load we have calculated taking 250 kilonewton per meter cube for the concrete unit weight. 6 meter thick ceiling we have taken, ceiling plaster, that is at the bottom of the slab, and 30 millimeter thick floor finish, that is at the top of the slab. Taking that, we are getting dead load 3.989 kilonewton per square meter, and live load that we have taken 4 kilonewton per square meter, which we can get for a specific purpose. Since it is not mentioned, we have taken 4 kilonewton per square meter, but for a specific purpose for that particular building, then we can get the appropriate loading from IS 875. Okay. The next one, load on beam. So, we are getting this one, that is kilonewton per square meter, that is on the slab. Now, we shall take the load on beam, individual beam. That means, if we go back, so if we come to this problem, that means we shall get the one so we shall get this is the square area for on the slab unit square, and we have that load from both sides. So, if we take this one, we can get the load 3.989 kilonewton per square meter, 3.989 kilonewton per square meter for dead load, and for live load 4 kilonewton per square meter, and which you are getting within this area. Within this area you are getting this load. Okay. So, now we have to take the loading on the beam, load on beam. So, how much is the load on beam? So, dead load for slab that we have already computed, and that we are assuming, and here we have assumed certain rib depth, that is 250 millimeter. So, we are getting an 5% extra for plastering, lot of other things. So, we can get 13.607 kN/m. Total live load 4 into 3, because spacing of beams 3 meter. So, 4 into 3 12 kN/m. So, you can get along this length we are getting that how much 12 kN/m and 13.607625 kN/m for dead load, and we have done up to this. Let us continue the number 3. Now, we have to take that factored load. And we have to calculate also factored load, then moment, bending moment, and shear. How much will be the factored load? Let us say WD, or we can take say WF, the design load, that factored load, which will be equal to, now we shall multiply, because since it is not mentioned, because we are taking only dead load and live load. So, we shall multiply with 1.5. So, which comes as plus live load equals 38.41 say kilonewton meter. What about moment? Our beams are simply supported on the masonry wall. There is no moment on two supports, because it is just simply supported. This is a case of simply supported beam. So, we can take the moment at the mid span, and we need the effect, we call it effective span. Instead of talking this one, we call it say effective span. What is that one? Our code says, even though we know say here, even though we know what should be the your effective span, that we have to find out, because it is dependent on that, not only that you say center to center of the beam, but it is dependent also effective depth also. So, out of that minimum one we take it, and here we are taking this one, unless otherwise specified, it is not mentioned, we shall take the center to center of the wall, center to center of the wall, that we shall take. So, we shall get moment, that mu equal to Wf times Le square by 8. So, Le will be equal to this one given here 5 I think we have missed it, right. So, that data let us take that one, say 5.5 meter. That 5.5 meter is the space, that your distance center to center between two walls, and that is the span, effective span, we shall take it here. So, equals 38.41 times 5.5 whole square by 8 equals 145.23 kilonewton meter. What about Vu? That shear force, design shear force, we shall take WLE by 2 equals 38.41 times 5.5 by 2, which comes as 105.63 kilonewton. So, this is your moment for which you have to design, and this is your shear force after the factored load. This is the design load. So, after multiplication of 1.5, if it is if you have seismic load, earthquake load, wind load, then appropriate factor we have to use. Next one, number 4, that effective width and depth. Now, we have to mention that what is the effective width of this flange, that we have to mention. Where from shall we get it? Already we have mentioned for T beam. So, we shall use this formula. If it is T beam, that we shall use it, and that is available in the code. If it is L beam, then we shall use this one, and if it is isolated say beams as per our code, for T beam we shall get this formula, and let me mention the other one for L beam. So, here in our case already I have shown while designing the T beam. In our case we shall use this formula. So, what is BF? BF equal to lesser of A L by 6 plus BW plus 6 DF, which comes as 5.5, let us say E here, divided by 6 plus 0.25 plus 6 times slab thickness 125 millimeter, which comes as 1.9166 meter. Let us take 1.917 meter. B center to center distance of beam, and which equal to spacing, that is 3 meter, and we have to take out of this lesser of this one, that which one is the minimum. So, BF equal to 250 equal to 1.917 this one meter equal to 1917 cell millimeter. Let us write down. What about your overall depth? This is a 1, this is the effective width. Number 2, we are interested to find out the effective depth. So, overall depth equal to, let us take, we have assumed 250 millimeter is the wave depth plus 125 millimeter is the slab thickness, which comes as 375 millimeter. Effective depth, if we assume that we shall provide 20 mm dia bar, assume 20 mm dia bar that we shall provide. So, effective depth equal to 375 minus clear cover plus 5 by 2, which comes as 375 minus 25 minus 20 by 2 equals 340 millimeter. In this case, what we can do, I am always mentioning this the other way. In books also you may find out that they are directly they are assuming the effective depth, that also you can assume. instead of assuming that effective overall depth and then coming to the effective depth, you can also assume that effective depth and then go to the overall depth. But why I prefer this one, because finally we have to provide overall depth, and overall depth should be some say regular number. That is why I prefer that let us assume overall depth, and let us also assume that we shall provide which type of bar, which diameter bar we shall provide. On the basis of that, we let us calculate that your effective depth, because effective depth can be any number, but whereas overall depth should be at least I prefer in multiple of 25 or maybe say multiple of 10 also. It is dependent on the designer. So, if we assume that we shall provide overall depth in multiple of 25, so let us assume overall depth and come to the effective depth. So, we have got that your say overall depth. Then what about your mu then? We know that mu equal to 0.36 FCK x by d 1 minus 0.416 x by d BF, here in this case BF, because we are talking say your that T beam BF times d square. If we rearrange this one, then we can get this formula. So, if you like to remember this one also, you can remember plus minus root over 1.2 whole square minus 6.68 mu divided by FCK BF d square. There are so many other ways also one can remember directly, instead of coming from the first principle always using this formula. You can remember this formula also if you like. So, we can write down x by d equal to 1.2 minus 6.68. Let us write down the full thing, 145.23 into 10 to the power 6, we are making everything in Newton millimeter, divided by 20 times the width of the flange 1917 millimeter times the effective depth computed, which we are going to provide. So, that is 340, which comes as therefore, x by d, one case x by d equal to 0.095 and x equal to 0.095 times 340 equals to 32.3 less than df, depth of the flange or slab, which equal to 125 millimeter. So, in our case it is that as if it is a rectangular beam. So, we can take this one, say your x 32.3. So, it is less than, it is within the flange. So, it is nothing but your, we can say it is a case of rectangular beam only, though we have taken T beam. So, we can use the formula. So, how much will be the steel provided? Number 6, say steel to be provided area of steel equal to mu divided by 0.87 Fy, the stress in steel, d minus 0.42 xu or x, that is the one lever arm, which comes as 145.23 into 10 to the power 6 divided by 0.87 times 415, that Fe 415 the steel, 340 minus 0.42 times 32.3 is the that your neutral axis depth, which comes as 1232 square millimeter. So, we can provide four numbers of 20 torr, and so what is the AST provided? Area of steel, this is area of steel computed, this one. So, area of steel actually provided equals 1256 square millimeter. So, we are providing 1256 square millimeter, little more. So, I think this is acceptable. What about your so we can provide that percentage equal to 1256 into 100 divided by, here we shall take it not on the basis of wave, rather we shall take it on the basis of not on the basis of flange width, we shall take it here that wave width of the wave. So, 250 times 340. When we shall take the percentage of steel, we shall take width of the wave equals 1.47%. Our code says that minimum steel, that should be 0.85 into 100 divided by Fy. So, this is our code says. So, 0.85 times 100 divided by 415, which comes as say 0.2%. So, our that steel provided, that is 1.47% greater than the minimum steel required. What about the shear reinforcement? I think we can, this one we can take it as a check. Let us take this one as a check. So, number 7 say check on the steel, that how much you are providing and whether it is permissible, whether it is within the limit. So, that we are checking in this case. Number 8, let us come to the same problem, the shear reinforcement. How much is our VU? That is 105.63 kilonewton. Percentage of tensile reinforcement, already we have computed 1.47%. What is our that tau c max, maximum shear stress? And that where from we shall get it? That we shall get it, refer table 20 IS 456. And you should always mention that whenever you are mentioning that code, you also mention the year, because different year, say 1978 IS 456. So, immediately that one you have to mention the year also, otherwise it is not complete, because there are so many revisions. So, 1978 may have some other say number. So, that is why you should always mention the year of publish, that when it is revised. So, maximum shear stress we are getting 2.8 Newton per square millimeter. That means, if that our nominal shear stress it comes more than that, then we have to change the section. So, tau v equal to VU by B times D. What about this B? B is the width of the wave. B is the width of the wave. Though we are talking say your T beam, but here we have to take B as the width of the wave. Vu equal to 105.63 into 10 to the power 3 divided by 250 times 340, and it comes as 1.2427 Newton per square millimeter. So, it is less than 2.8. So, no need of changing the section. Now, what about whether we need shear reinforcement? What about the shear reinforcement? That we have to find out. We can get it that 100 AST by BD, and we have tau C, and that we shall get it in table 19 IS 456. So, let us write down table 19 IS 456 2000. When you do the design, you always mention that the reference clause or table of the code, that always you have to mention, and we generally we do it in this side. In the right hand side, generally we refer all those things. So, we can get it because it is 1.47. So, 1.25 if it is the tensile reinforcement percentage, which comes as 0.67, and if it is 1.5, then it is 0.72. This one, the part of the table 19, so appropriate that values 1.25, 1.5, because you have to take it 1.47. So, tau C you will take it linear equal to 0.67 plus 0.72 minus 0.67 by 0.25 times 1.47 minus 1.25, which comes as 0.714 Newton per square millimeter. So, this is the tau C which will be taken care of by concrete. The shear stress, this portion, the tau C times BD, whatever shear force we shall get, that one will be taken care of by the concrete, which will be due to the that aggregate interlocking, then compression of the concrete zone, and also the dowel action of the reinforcement steel, the tensile reinforcement steel. So, that composition total we shall get it from table 19, how much we shall take, and that is coming here tau C equal to 0.714 Newton per square millimeter, and which is less than tau V, the one we have computed. So, this is your tau V which we have computed, which is coming as 1.2427, which is greater than 0.714. So, we need shear reinforcement. So, in our case we can write down that tau V greater than tau C, but and tau V less than tau C max. So, no need of changing the your say section, but we have to provide shear reinforcement. So, shear the concrete due to concrete say, and let us say that one VC. So, VC equal to 0.714 times 250 times 340, which comes as 60.69 kilonewton. Shear to be taken by steel, VS say equal to VU minus VC 105.63 kilonewton minus 60.69 kilonewton equals 44.94 kilonewton. What about VUS? Let us go to the next page then. VUS, that is as per the code 0.87 FY times A is V times D divided by SV, the spacing. ASV by SV equal to VUS in our case divided by 0.87 FYD, or ASV by SV equal to 44.94 into 10 to the power 3 divided by 0.87415 times 340 equals 0.366. This is the one that ASV by SB we can get 0.366. If we use, let us say, use 8 mm Tor. So, ASV, and we shall use two-legged. Therefore, ASV equal to 2, which will be equal to say 2 into 50 equal to say 100 square millimeter. We can write down ASV by SV equals 0.366. So, SV equal to ASV by 0.366 equal to 100 by 0.366 equal to 273 millimeter. SV equal to 273 millimeter. So, let us write down the spacing SV 273 millimeter. We are using 8 mm Tor two-legged. What our code says, that maximum spacing A 0.75D 0.75 times 340 equals 255 millimeter. B not greater than 300 millimeter, our code says. So, minimum of this, minimum, or I can say lesser of the above two equal to 255 millimeter. So, it is governed by this one. So, we can provide, though it is maximum spacing here 273, here 255, here 300. So, we can specify use 8 Tor two-legged at the rate of 250 millimeter center to center. Okay. So, this is the one that we are providing. It is always better that after this, it is always better to summarize our result. It is always better to summarize our result. So, what we can do then? We shall provide the T section we have here 125 and this one 250, we have 420 and the stirrup Other two bar we are just providing, say, that we shall we need not specify here, but anyway, because for our design we shall not specify. So, we shall get 250 420 torr, 8 torr, 2-legged at the rate of 250 millimeter center to center. Concrete M20, steel Fe415, that only we have taken Fe415. Anyway, so that we have used this one. Clear cover, let us mention 25 millimeter. Main longitudinal tensile reinforcement 420 torr, stirrup 8 torr at the rate of 2-legged, mention 2-legged at the rate of 250 millimeter center to center. So, this is your the summary of the results. It should be at the end we should summarize the whole thing, because finally that this one only will go for drawing or to the draftsman, because they do not need any calculation, all those things. So, it should be very, very clear. And though it is not mentioned, so we can provide, let us complete this one, that hanging bars. Let us take here the 210 torr. This is not in our calculation, it is not mentioned. To complete this figure, let us take this is 210 torr, because it is not, we are just providing the minimum one. So, we can provide 210 torr. Okay. So, this is the that your whole design, that step by step that you have to make it, that whole design step by step you have to make it for your, say, flexure as well as for shear. Let us solve one more problem. I think that one will give you that your for nominal shear. So, design of stirrups for nominal shear. Let us take B equal to 250 millimeter, D equal to 450 millimeter, longitudinal tensile reinforcement that is here 520 torr, VU the shear force, that is the factored one, 60 kilonewton, concrete M20, steel Fe415. Okay. So, what is the effective depth? Effective depth equal to 450 minus 25 is the clear cover minus the 20 by 2, that is the diameter of the bar, half of the diameter, which comes as 415 millimeter. area of steel AST equal to 5 into pi by 4 20 square equals 1570 square millimeter. Let us write down here percentage of steel P 1570 into 100 divided by 250 times 415. 415 is the effective depth. Please note this is 415 is the effective depth which we have computed here, which comes as 1.513 percentage. 1.513 percentage. Okay. This P we shall take it for our that tau C, to calculate tau C. What about the shear force? Number 2, the tau V equal to VU by BD, VU equal to 60 into 10 to the power 3 divided by 250 times 415. This 415 is the effective depth, please note, not the one the steel. 0.578 Newton per square millimeter. Tau C max from table 20 of IS 456 2000, which comes as 2.8 Newton per square millimeter, less than tau C max. From table 19 we shall get 100 AST by BD and tau C, that we shall get 1.5, we are getting 0.72, this is in Newton per square millimeter. 1.75, 0.75, so tau C equal to 0.72 plus 0.75 minus 0.72 divided by 0.25, 1.513 minus 1.5 percentage of steel, which comes as 0.722 Newton per square millimeter. So tau C we shall get it as 0.722 Newton per square millimeter and tau V 0.578 Newton per square millimeter. So if we write down tau V 0.578 Newton per square millimeter, tau C computed 0.722 Newton per square millimeter, tau C max 2.8 Newton per square millimeter. So we can write down tau V is less than tau C and less than tau C max. So we can write down only nominal shear reinforcement is required. What our code says? Our code says that what should be the nominal shear reinforcement. We can get it in clause 26.5.1.6, that we shall get it in 26.5.16 of IS 456 2000. Here that A is V by B is V, 0.4 divided by 0.87 Fy, 0.4 by 0.7 Fy. We can get this value, or A is V by SV equal to 0.4 B times 0.87 times 415 equals 250 times 0.87 times 415. So we can get it let us provide use 8 torr two-legged. So, ASV equal to again equal to 100 square millimeter. SV equal to ASV by how much is this value? ASV by SV, which comes as 0.276. So, ASB by SB. So, from there we can find out 0.276 equal to 362 millimeter. What about the spacing? Maximum spacing? A 0.75 D equal to 0.75 times 415 comes as 311 millimeter. B not greater than 300 millimeter. There is a numerical value mentioned in our code. So, we have to provide the shear reinforcements T rough 8 torr two-legged at the rate of 300 center to center, because we are taking 300, that is the one minimum, and here 311. So, we have to provide 300. So, 8 torr two-legged at the rate of 300 center to center, that we have to provide, and that we can get it, that is the one minimum, that nominal reinforcement. So, in your problem that which you have given, so there you have to take this, you have to calculate according to these steps. Okay. So, this is all regarding your say beam design, that your flexure as well as say shear, and it should be complete and it should follow that steps, and you should not keep everything in your calculator only, that means only the final result, not that one, because sometimes you have to produce your design calculation also. And there is another one, say the designer has done it, sometimes it has to be proof checked, that whether the calculation everything done according to IS codes, according to the analysis methods design. So, that is again proof checked. So, it should be vetted by somebody else. So, that is why that your calculation, all those things, if you do everything in your say only calculator and put the result, then it will be difficult. Maybe it will be difficult for you also, even after say maybe 1 month or 2 months also, or if it is more, then it will be more difficult. So, that is why it is a good practice that you have to refer your clause of IS 456 or any other code which you are using. That is number 1. Number 2, that your calculation, you write your formula first, equation first, and what are the, if you remember everything fine, if the say ASV, that is the convention, if you follow that ASV is the for the shear or shear, that your say area of steel, AST, that is the area of steel for the tensile reinforcement. If you mention that way, and if you can have in the very beginning of your report the list of that your say symbols used, so that is fine, and otherwise you have to mention what is that AST, ASV, all those things that you have to mention, that is number 1. So, what you have to do, you have to use your formulas, you have to write your formulas first, and then you put your numerical values in the corresponding position wherever you have used that your formula, that your say different variables, and then you write down the final result, not the one you have used your formula, written your formula, and then finally you are writing that your say equation and final end result, then it will be difficult for you to check it if it is required. This is that always you do it, and you use and you write down your that clause, tables, whatever you are using. Say for example, in table 19, whenever using, I am writing that one your say your the percent of steel and the corresponding tau c, again percent of steel and corresponding tau c, that I am mentioning, and then I am again writing that one, because it helps in future. Otherwise, in the calculator itself I can do it, but end result sometimes if you do any mistake, then again it will be too much confusing. So, that you avoid. This is one part. The second part, that not necessarily that your section will be simple rectangular or T-beam or L-beam, not like that. Sometimes you have to design your section which may be some say your different shape. Say it may happen like this also. If we take this one up to this, maybe due to from the architectural point of view, or maybe from some other view, say we would like to provide your say cables, all those things through that. So what happened here, this is also another section. So here again it is nothing but the T section, because that your neutral axis, if it comes within, if you can provide within the flange, then there is no problem, because then it is a simple say rectangular one only, and the other part, the concrete, is not taking any load or anything, any moment. So whatever reinforcement you are providing here, so that is the one your area steel. So it is nothing but, again you can say this is nothing but T-beam, or again you can come back to that one. Otherwise, if it comes the other option, the neutral axis, so then you have to do that your calculation. So in this case, it is always preferable that I shall keep the neutral axis. That is one way of the tricky solution, that we are providing the solution within that limit, and so our calculation, other things will be easy. So this is your one problem. It may happen, say sometimes it may happen, though it is not one, but sometimes it may happen that it can be something like this also, the other way. But even then, your reinforcement, whenever you are providing the reinforcement here, but this one will not come into picture when that your neutral axis is within this limit. So that way you can solve your different problems that you can solve. So your problem for exam purpose, other things, that this type of cross section may come. Okay, that also you can consider. Okay, so thank you. Okay.